Hello and welcome to this video about algebraic integers. This is their definition, that they are a type of number and they can be any complex number that is a root of a monic polynomial with integer coefficients. Here are some examples of monic polynomials with integer coefficients. A monic polynomial is a polynomial whose leading term has a coefficient of 1. We wouldn't write out the 1 in front of the leading term. We'd just write out the leading term, and all of the rest of the coefficients have to be integers, which could include 0 and -1. So in this video, we'll investigate which numbers are algebraic integers by trying to find monic polynomials that have these numbers as their root. We'll have a look at the number 1 and ask if it is an algebraic integer. And so it is, because we have found a monic polynomial that it's the root of, which is x minus 1. Is 0 an algebraic integer? Yes, it is, because x written by itself is a monic polynomial, for which 0 is the one and only root. And you can probably guess that 2 is an algebraic integer, because x minus 2 is the smallest monic polynomial that it is a root of. -1 should be an algebraic integer, because its corresponding monic polynomial is x plus 1. I'll pick a random larger number to investigate this time, and you should see a pattern emerging, that any integer is an algebraic integer, and that the corresponding monic polynomial should be x minus this integer. So we can write this down more formally for any integer. If n is an integer, then it is an algebraic integer, and its corresponding monic polynomial should be x minus n. Let's look at some different types of numbers. Let's look at the imaginary number I. Is I an algebraic integer? Yes, it is, because it is the solution to this polynomial x squared plus 1, and its opposite minus I is also a root of this polynomial, and so it is an algebraic integer too. And 2i should also be an algebraic integer, because we could find a monic polynomial for it in a similar way. X squared plus 4 is the monic polynomial that it is a root of, so 2i is also an algebraic integer. We can generalize this and say that I times any integer is an algebraic integer, because the monic polynomial that it is a root of is always x squared plus n squared. Let's look at this irrational number root 2. Is this an algebraic integer? Yes, it is, because this is the monic polynomial that it's a root of, which is x squared minus 2. We can show that the square root of 3 is an algebraic integer in a similar way. We can show that it is an algebraic integer by constructing this monic polynomial which it is a root of. And we can show that the square root of any integer is an algebraic integer. And we can do this by constructing this more generalized monic polynomial in a similar way as for the last two numbers. The set of all algebraic integers is a ring. This means that for any two numbers that are elements of this set, their opposites, sums, and products are also elements of this set, and 0 and 1 are also elements of it. We've just shown this earlier, but we can say that they are algebraic integers because this set is a ring. So is this number an algebraic integer? Yes, it is, because it is the sum of two algebraic integers. So we don't need to construct a monic polynomial for which it is a root. This is how we'd construct this monic polynomial. We'd multiply these two expressions together, which would give us this sum of squares. which would give us this expression which looks like it will be a monic polynomial. And so it is. So we've shown that this number is an algebraic integer twice, first by using the ring properties of this set, and secondly by constructing a monic polynomial for it. Is this number an algebraic integer? Yes, it is, because it's the sum of two algebraic integers that we looked at earlier, and because this set of numbers is a ring, then the sum of two algebraic integers is also an algebraic integer. Let's find the monic polynomial for which it is a root of. This is the general formula for the monic polynomial for a root of this form. We can then substitute these specific values into it. We still have to simplify this polynomial. So this is the monic polynomial for which this number is a root. Can you tell, just by looking at this number, whether it's an algebraic integer or not? It is, because it is the product of two algebraic integers. We don't have to expand or simplify this expression to work this out. Is this number an algebraic integer? Yes, it is, because we can extend the sum rule, so that the sum of any finite number of algebraic integers is also an algebraic integer. If we rewrite this number with these brackets, then the first number in brackets is an algebraic integer. So after the next number is added to it, then it is an algebraic integer again, using this addition rule. So is this complicated looking number an algebraic integer? Yes, it is, because we could immediately find the monic polynomial that it is a root of. Here it is represented in the complex plane. It is one of the algebraic integers that we need extra sine and cosine terms for, and can't be written only using radicals. That includes square root and cube root symbols. In fact, all of the complex number solutions to this equation that are represented on this complex plane are algebraic integers. They can be added to any sort of other algebraic integer so as to make new algebraic integers. Now, is this fraction an algebraic integer? It turns out that it isn't, and we need a more complicated proof to demonstrate this. We'll suppose that if this monic polynomial exists for it, then this equation will be true, a0 to an being the coefficients of this polynomial, and an being equal to 1. We can then manipulate this equation to be this, and manipulate it again into these two fractions. I'll just write it again up here after clearing the screen. We can multiply both sides by 3 to the power of n minus 1. Then we can multiply both sides by 3 like this. And so this complicated expression inside the brackets must be an integer, because it contains only sums and products of integers, and may be expressed as the integer x. But the number 3 can never divide 2 to the power of n, no matter how finitely large n is. So the integer x can't exist, and so the coefficients of a0 to an can't exist either. So the monic polynomial can't exist, so that 2/3 is a root of it. So 2/3 isn't an algebraic integer. We can easily adapt this proof for any fraction. Now to create formulas for finding monic polynomials that have these numbers as their roots. The monic polynomial for this number is created from this expression, which is equal to the sum of these squares, which is equal to this expression. So this is the monic polynomial that has this number as a root. So now to get the monic polynomial that has this number as a root, which will be a bit harder to find than for the last number, we'll use this polynomial with degree 4, and we'll substitute this value in for x. These are what all of the powers of x are equal to. We'll then substitute this value for x into this polynomial to give us this complicated expression. I'll just write it out at the top of the screen here. The terms for x and x cubed contain only radicals like root p and root q and can be eliminated, so a1 and a3 can be set to 0. Since the polynomial is monic, then a4 can be set to equal 1. So this polynomial can be simplified to be this. And I'll rewrite this equation out again at the top of the screen. Now we'll have to find the values of a0 and a2 for which the radical root pq cancels. We'll end up with these two equations when we separate out radical and non-radical parts. We can rearrange these equations so that the variables a0 and a2 are on the left-hand side, while the rest of the equation is on the right-hand side. I'll just write this equation up at the top of the screen here. I can write these two equations out as this one matrix vector equation, and solving it gives us these values for a0 and a2, which we can substitute back into the polynomial to give us the monic polynomial for this number. So I hope that you have enjoyed this video and have learnt a lot from it. Good luck in your quest to learn this sort of mathematics. Please click like and subscribe if you enjoyed this video, and please leave all of your thoughts, opinions and advice in the comments. And thank you for watching.